Monte Carlo simulation, a super simple approach to solving complex problems. By the end of this video, you'll know how to set up Monte Carlo simulations in Python. You'll also know a bit about how you might go about structuring your code to maximize reuse. The example we're going to look at is taken from a computer simulation book by Mike Pidd. I highly recommend checking this book out, available in all good libraries. We're going to take a look at an investment problem. Business is going to invest $10 million into a new production line, and it's generated some forecasts of cash flows over the next 5 years based on that product line. What we need to do is evaluate, is that a good investment or not? Is it going to return a profit or is it going to return a loss? To do that, we're going to need to convert the value of those future cash flows into current money. We need to remember the time value of money. So to assess the value of that investment, we need to discount those future cash flows into their present value. We need to sum all of those together along with the initial investment to obtain the net present value of that investment. The formula for present value of a future cash flow is the future value divided by 1 plus the discount factor r, all to the power of n, the number of time periods in the future, in this case, years. All of the code we use today is available in a notebook on GitHub. I'll link to that in the description below. If any of this is useful for you, then perhaps you could click that like button and subscribe to the channel. To help with our analysis, I've defined some Python functions. The first is the PV function. That's going to return a discounted value at a rate we define. So it accepts the future cash flow value, the discount rate, and the number of years into the future. And then we use our present value formula to discount that cash flow into current day money and return it to the user. Net present value, or an NPV function, then calls the present value function in a loop. So we pass in our future cash flows as an array and the discount rate we'd like to use. And then we've got a list comprehension here that just loops through each of those cash flows, calls the PV function for each, passes in the future value, the discount rate, and the years into the future. And then we sum all of that together to return the net present value. I've also included a CSV file that contains forecasted receipts into the future, going forward 5 years. The business has split that into 3 scenarios: an optimistic high return scenario, a more likely median scenario, and a low return scenario. The function load receipts simply accepts a string value and loads that CSV file as a pandas data frame and returns it, and we make sure that the index column has been set to the year. And then finally, we have a plotly function that's going to accept a NumPy array of cash flows, and it's going to plot the cumulative frequency distribution of those, as well as a few other things we'll talk about later. We're going to use this with our Monte Carlo simulation. The first thing we'll do is a deterministic analysis. So I've set up a few values to start up with. Our default initial investment, which was $10 million. It's a negative value because that's something we're paying out rather than receiving. Our discount rate is 10% or 0.1, and we're looking at only 5 years into the future. So we can load in the receipts in our CSV file as a pandas data frame. I've called that expected receipts. We then have some code which constructs a list of cash flows, including our initial investment for a given scenario. We can then pass those cash flows along with the discount rate to the net present value function and return our expected return on investment in today's money. So for example, in the pessimistic or low scenario, we'd expect to make a loss of nearly $3 million. So we can see that it's going to range between $4 million and negative $3 million, possibly with the most likely scenario in about $1.2 million. So the issue with this type of analysis is it does not give you information on the likelihood of each of those outcomes. So an alternative to the deterministic analysis is Monte Carlo simulation. The name is an analogy to gambling in a Monte Carlo casino. So there's an element of randomness in the results that we're going to see. In fact, what we're going to construct is a stochastic model where we're going to sample from different statistical distributions in order to obtain a result. This means that each time we run the model, we'll see a slightly different output. For example, here I've constructed a simulation experiment which is going to contain all of our default values. We'll go through that code in a moment. And then I've performed a single run of the model. So all of the complexity at the moment is hidden behind this function single run. We ran that, and what we realized was a net present value of less than 0. So we've made a loss in this particular run of the model. Now, if I run the model again, we obtain a different result. And again, by chance, we have seen a loss. And this time that we've run the model, we've seen that we've made money. In fact, we've made $1.6 million, which is quite a nice return. So rather than doing it painfully like this with a single run after another, we can run Monte Carlo simulations in a loop. We tend to call that multiple replications of the model. So hidden behind this function, multiple replications, is a for loop that's going to repeatedly call the single run function. In fact, we're going to run 5 replications of that. That's returned a NumPy array called results, and we can see different realizations of net present value for that Monte Carlo simulation. Let's run a few more. So now I've run 10,000 replications of the model. So we've obtained a distribution of output. We could look at the mean of that result. So we can see that on average, we would expect to obtain $840,000 in our return in today's money. Alternatively, I've created a function called results summary where we can pass that data and we'll see some information about the distribution. So, okay, we've got the mean of the 10,000 replications, but we can also see that there is a chance of making a loss. And we can also see the median. So it's a fairly symmetrical distribution, and we can see the standard error. Now, we really need to go a bit further than this within an investment decision. So let's plot the cumulative frequency distribution and have a look at the break-even point of the project. So here we can see an interactive chart plotting the cumulative frequency. So the x-axis is our expected net present value in millions, and our y-axis is the cumulative frequency, or the probability that that outcome will occur. Our green star here is our break-even point. And we can see that there's about a 12% chance that we'll break even on this project. We've got a 12% chance we're going to make a loss and an 88% chance we're going to make some money here. The red line is the mean of the distribution, and we can see that it's almost symmetrical about that. The median is just a little bit higher. The beauty of Monte Carlo simulation is its simplicity. To obtain that randomness within our output, we've defined 5 triangular distributions. The parameters of each triangle are the low, the most likely, and the high scenarios for that year. So I've created a class called triangular, and I'm passing in my low, my most likely mode, and high scenario values, and I'm also passing in a random seed. That's going to enable us to make this a repeatable experiment. We can control everything about what's happening. Inside the initializer of the class, we're creating an instance of NumPy's default random number generator, and we're seeding that number generator with the seed that we've passed in. We're also storing the low, the high, and the most likely value of that triangle. A triangle distribution draws a triangle between those 3 points, and NumPy is going to sample from within that triangle, biased towards the mode. I've defined a function called sample, and we can either obtain a single sample by allowing size to equal none, or we can obtain multiple samples in one go by specifying that size parameter. That is all that's going to do, is call the triangular method of the random number generator and pass in the low, the mode, the high, and the size. The eagle-eyed of you will have seen that I defined 2 other notebook level variables. The first was the number of streams. This is basically the number of pseudo-random number generators we will need to create in our Monte Carlo simulation. In this case, it's equal to n, the number of years we're going to simulate. I'm also specifying a default seed. This is the main seed. We're going to pass this to an experiment class, and that's going to set up our 5 triangular distributions. The seed enables us to get a reproducible result across each of those random number generators. The experiment class is simply for convenience. It's an abstraction that allows us to store our parameters for a particular experiment in the model and also the random number generators. So we're going to pass in our initial investment, we're going to pass in our discount rate, we're going to pass in our investment horizon, we're going to pass in a path that's going to link to the potential receipts in the future, and we're also going to pass in information about our random number generators and seeds. This is useful because we might, for example, want to compare scenarios with different discount rates. The initializer of the experiment doesn't do anything complicated. We're just going to store those parameters that we've passed in. We're going to create another member variable called dists. This is a dictionary, and that's going to contain each of the triangular distributions. The keys within the dictionary are going to be the years, and that's going to enable us to pick the correct distribution depending on which year we're simulating. The first method in the class is called setMainSeed, so we can pass our seed in externally if we wish to. We'll see that'll be useful when we switch between the replications of the model. So we could run replication 1 with a seed of 1, replication 2 with a seed of 2, and so on. We'll store that seed and we'll initialize sampling. Finally, the initialize sampling method creates the triangular distributions. Before it does that, it creates n non-overlapping pseudo-random number streams. We do that using NumPy's seed sequence class. So we only need a single seed. We pass in that seed. It can be a low quality seed like 0 or 1 or 2, and NumPy will create a set of high quality seeds when we call the spawn method of that seed sequence. So if we need to create 5 streams, we simply pass in the number of streams we'd like to create, i.e. 5, and it will return a list of seeds that we can then pass to each triangular distribution. We then create each of the triangular distributions. We're populating our dictionary, so we create our keys incrementally as we go along. So we've got in a string the year, and we're passing in I plus 1 so that each key is unique. We're creating an instance of the triangular distribution. For that particular row in the pandas data frame, we're creating the low, the median, and the high parameters, and we're setting the particular seed depending on which year we're using. The Monte Carlo model class is also very simple. So we're going to pass in an instance of an experiment with a given set of random numbers. We'll store that internally because we have a function called simulate net present value. That's going to return a float value, which will represent the net present value of that simulated replication. So first of all, we create our list of cash flows. So we have a list comprehension here. We're going to loop from I through to the investment horizon. On each iteration of the loop, we call the sample method of the triangular distribution allocated to that year. So in the first loop, we'll look up year 1, the triangular distribution, and call the sample method and store that in the cash flow list. Next, we call the net present value function, not forgetting to include our initial investment along with our cash flows, and we also pass the discount rate to the function, and we return that to the calling code. Now, to make this a reusable and repeatable experiment, I've done a small trick here. I've created a wrapper function to sit above that simulate net present value method. That's called single run. We pass in our instance of experiment. We pass in the replication number that we're going to run. That's going to be used as the seed for the experiment. So the first thing we do is call the experiment's set main seed method and pass in that replication number, or in other words, the new main seed. That's going to set up our 5 non-overlapping streams of pseudo-random numbers, which we'll use to sample from the triangular distribution. We'll then pass that setup experiment to the net present value model and call its simulate net present value function and return the result. So for example, if I wanted to obtain the result from replication 1, I will call the single run function and set rep underscore I equals 1, run that, and I would obtain a positive result of $0.5 million. If I change that to 2, I would get a different result. I would get $1.1 million. If I ran that code again with no changes, I would get the same result. So you should be able to quickly see that in order to run multiple replications of this model, all we now need is a for loop that wraps around that single run function. I've again put that in a function for you. I've called that multiple replications. We'll pass in an experiment and we'll set the number of replications we would like to run. The default is 5 just to make things easy. And the result will be returned as a NumPy array of net present values. So the code again is a list comprehension. We're going to loop from rep to number of reps, each time calling the single run function, passing in that replication number as our main seed and storing the results in a list called results. I'm going to return that, casting it to NumPy, just that makes it a bit easier for analysis. And then finally, just to clean up the result, I've got a simple function called results summary. That's going to accept that array of simulated net present values, but will return a pandas data frame. So it'll initially cast that data to a pandas data frame and call the describe method and transpose. That'll give us the mean, the standard deviation, the min, the max, etc. But another thing that's useful when thinking about a mean is its standard error. That's not calculated by default. So there's a bit of calculation here that includes that for you, and we return the summary table. So now we can run as many multiple replications of our model as we want. We can run as little as 5 and obtain a small array, or we can run as many as 100,000. The structure we've set up for our Monte Carlo simulation model means it's now really simple to run multiple experiments. For example, I might want to run an experiment where the discount rate is different from the default. So the original problem stated a discount rate of 10%, but what about if it's 3.5%? What would the results look like then? Well, it's relatively simple to create that experiment, then rerun your multiple replications and look at what that means for the mean result. If you'd like to learn more about sampling in NumPy and Python, you need to watch this video that's on the screen now. See you next time.